Welcome to my channel. These days we are discussing important questions chapter wise. So, in today's session, children, we'll be discussing D block elements, all the important questions as board exams are approaching. So, please prepare accordingly and watch till the end. See, the first question is group 12 elements are not transition elements. Why? Now, group 12 elements means we are talking about zinc, cadmium, mercury. They are not transition elements. Now, first we should know what are transition elements. Transition elements are those in which d orbital is partially filled in atomic or in ionic state. In ionic state. In any one of the state, D should be partly filled. That means it should not be D10. If it is D10, it is not transition element. Right? So first you will write transition elements are those in which D orbital is partially filled in atomic or in ionic state. Right? Then you will write that in the atomic state, the configuration of group 12 elements is N-1D 10 NS2. That means D is completely filled. And let's see in ionic state what it is. So I've taken example of zinc, right? You can take zinc. Configuration of zinc in the atomic state is this. Ionic state is 3D10. That means in both the states it is having D10. Since they have D10 configuration in both atomic as well as in ionic state, they are not transition elements. Got it? So you'll be first writing transition elements definition. Then you'll take particular example of that. Say zinc, it is having D10 in both the states, so it is not a transition element. Right? So you can say it is a D block element but not transition. A similar question can be asked like this also, that all transition elements are D block elements, but all D block elements are not transition elements. So in this also you will take example of group 12, right? Group 3 to 12, they are all D block, but 12 is not transition, rest all are transition. Fine. Next question, somewhat similar to this. Though group 11 elements have completely filled d orbital, they have completely filled d orbital, even then they are transition elements. Why? Now this is also somewhat related to transition. That means you'll be first writing transition elements definition, right? And then you will take example of this copper. Acha, this is also one question asked in NCRT, that is silver, though it is 3D10, it is transition element. Why? So a same answer will be there, but the question can be asked in a different manner. This is having D10, why are they transition? Or silver is D10, why it is transition? So you will write the example. If it is silver, then also you may write, or with reference to any transition element if they are asking, you will take example of copper. So how will you write? First transition elements definition, then you will write copper or silver's configuration in the atomic state, then in the ionic state, then you will write in atomic state it is D10, but in the ionic state it is not D10, it is partly filled. Since it is partly filled in any one of the state, means it is ionic state, so it will be a transition element, right? So group 11 elements we also call as typical transition elements because their behavior is typical. In the ionic state it is partly filled. Clear? We move on to the next question. Group 6 elements are hard. Now what is group 6? Group 6 is chromium, molybdenum, tungsten, right? And the general configuration is N-1, D5, NS1. How many unpaired they have? They have 6 unpaired. 6 unpaired because 5 of this and 1 of this. So they have maximum number of unpaired electron. It is a very important property of the transition elements that they have interatomic bonding. Interatomic bonding means one atom's unpaired electron pairs up with the another atom's unpaired electron. So more the number of the unpaired in one, more will be the chance of interatomic. That means in this case, one atom itself is having 6 unpaired. So 6 unpaired will pair up with the 6 unpaired of the neighboring atom. So more the number of the unpaired, more will be the chance of the interatomic bonding. so they are hard. Or you can be asked like this, group 6 elements, they have high melting point. Or you can be also asked, why is tungsten used in filaments? Because it is having high melting point. Why they have high melting point? Now you know they have maximum number of unpaired. More the number of unpaired electron, more are the chances of interatomic bonding, more hard it will be. Group 12 elements are volatile metals. Now what are group 12 elements? Means we're talking about zinc, cadmium and mercury, right? And their configuration we know is n-1d10 ns2. That means they have no unpaired electron. When they have no unpaired electron means no chance of interatomic bonding. No chance of interatomic bonding means they are volatile. That is why when these elements they are present as impurities with something else, they can be separated by steam distillation. They can, just distillation we can write, by distillation they can be separated, because they will have the less boiling point, right? They are more volatile, less boiling point, so they can vaporize faster. Clear? Now next question. The question says the melting point across the period first increases and then decreases. Why does the melting point first increase and then decrease? The answer lies in this. Just now I told you the interatomic bonding part. If they have more unpaired, there will be more chance of interatomic bonding. Less unpaired, less interatomic bonding. So this is the configuration. I've written the configuration for all third, fourth, fifth, sixth, seventh, eighth, 9, 10, 11, 12 groups. Right? So when you check their configuration, they are having 1 unpaired, 2 unpaired, 3. This is abnormal configuration. 5 and 1, 6 unpaired, 5 unpaired, 4 unpaired, then 3, 2, 1 unpaired and 0. So what is happening? The number of the unpaired electrons are increasing and then decreasing. Unpaired, because the d orbital can accommodate maximum 10 electrons, right? So suddenly it cannot be d10. So initially the number of the unpaired electrons are increasing. After d5, when d6 comes, the pairing of the d orbital begins. So when pairing begins, the number of the unpaired electrons are decreasing. And there comes one point where it is not having any unpaired. So the melting point is also related to the number of unpaired electron, right? So as per the configuration, how will you write the answer? You will write as per the configuration, the number of the unpaired electron across the period of first increasing, reaches the maximum and then starts pairing up. So when it starts pairing up, the number of unpaired electrons are decreasing. That is why the melting point first increases. As the unpaired increasing, a chance of interatomic bonding is increasing. After pairing, chance of interatomic bonding decreases. So the melting point also will decrease. Just now I discussed the question based on the melting point. This was the graph somewhat similar to this you have in NCERT also. Now, in this, there is another question asked, that is Mn and Tc. They exhibit dip in the melting point. Normally, first increasing, then decreasing. Right? This is the first series, that is 3D series. This is 4D series. This is 5D series. But for 5D, in 3D and 4D, you find there is a dip at Mn and Tc. So how will you write the answer? They have D5 configuration. When they have D5 configuration means they are stable. When they are stable, they will not have any ability to undergo, to have that interatomic bonding. If they are themselves stable, then they will not like pairing up with the other, right? So these two are the exceptional cases. Though just now we said more unpaired means more interatomic bonding. So Mn and Tc, because they are stable in D5 configuration, will not have a tendency to undergo that interatomic bond, right? Next question. The atomic radii across the period first decreases, then remains the same, then again increases. So if I write this 3D series, now what is there in 3D series? We find that D1, D2, D3, then D5, S1, like that it is. So first it is decreasing, they are saying, then it starts remaining the same, and toward the end again we find it is increasing. Why? They are asking the reason for it. Now first you will write that in d block elements, the last electron does not enter into ultimate shell. It enters into penultimate shell. So penultimate shell is the inner one, second last shell. So when electrons are added across the period, there are two things which are increasing. Number one, nuclear charge. With one electron, one nuclear charge is increasing. Shielding effect is also increasing. So there are two factors which are accounting for the size. So first, initially, nuclear charge throughout the period is increasing. Shielding effect increases, but in the beginning, the nuclear charge is, the shielding effect is not that strong. Why? Because one electron, second electron, the shield is not that strong. When the shield starts becoming strong, that means when D starts pairing up from iron onwards, when D starts pairing up, their shield becomes strong. Shield becomes strong means the effect of the nuclear charge will reduce. So initially, effect of the nuclear charge is more, so the size decreases. Thereafter, shielding effect becomes more because the shield becomes the strong. The electrons get paired up. So when they get paired up, so the shield is becoming strong. That is why both are countering, the effect of each other. After that, nuclear charge is trying to decrease the size, but shielding effect is trying to increase the size. So thereafter, it remains the same. But in the last, D10 configuration. So D10 configuration means completely filled d orbital, due to which there will be more interelectronic repulsion, due to which the size starts increasing at the end. Now, next question. Down the group, atomic radii first increases, then remains the same. That means when we move from 3D to 4D, size is increasing. After that, 4D and 5D, they have nearly same size. So I have written one part of this D block element. This is third group, fourth group, and fifth group. This is 3D series, this is 4D series, and this one is 5D series. So from 3D to 4D, size increases, then remains the same. Reason, in 5D series, after lanthanum, this is 57 atomic number, this is 72. In between, there are 14 lanthanides. In lanthanides, there is lanthanide contraction. So the effect of the lanthanide contraction is visible in all post-lanthanide elements, due to which, so you will write why it is remaining the same after that, due to lanthanide contraction. The post-lanthanides will have the small size. So from here to here it is increasing, but this is a post-lanthanide element, hafnium, tantalum onwards. So they become almost the same. And it is said that zirconium, hafnium, they have exactly the similar size. So they are also termed as the twins of the periodic table. Right? Next question. Transition elements exhibit high enthalpy of atomization, or you can be also asked like this, that why zinc has the lowest value of enthalpy of atomization. Just now I made a mention of interatomic bonding. Transition elements, they have large number of large number of the elements in which the d orbital is unpaired. Unpaired electrons are there in d orbital. Right? More the number of unpaired electrons in d orbital, more are the chances of interatomic bonding. So more interatomic bonding means the enthalpy of atomization will be more. Why zinc has the lowest enthalpy of atomization? You will write configuration of zinc as CD10 4s2. That means d orbital is completely filled. When it is completely filled, no chance of interatomic bonding. Now, if you are asked, transition elements exhibit large number of the oxidation states, why? You will write the configuration of the transition elements, and then you will write the energy difference between n minus 1d and ns orbitals is very less. Now, because the energy gap is less, not only the ultimate shell, but the penultimate shell also, the electrons can take part in the bond formation. So in them, both take part in the bond formation, ns and n minus 1d. As the energy difference is less, both can equally participate. So they exhibit large number of oxidation states. Sometimes you're asked to compare the transition and the non-transition element. Non-transition here means the p block elements. So you'll write down two differences between them. One, in transition elements, the oxidation state of the elements, they differ from each other by unity. They differ from each other by unity. Like for example, if I say Mn will exhibit all oxidation states from 2 to 7. 2, 3, 4, 5, 6, 7, all. So oxidation states are differing by unity, whereas here they differ by 2. They differ by 2. Like for example, if you say halogens, 17 group elements will exhibit the oxidation states. The range we are saying is -7 to +7. But what are the common oxidation states they exhibit? -1, that is the normal one. Then you say 1, 3, 5, 7. Right, that we have already discussed in the p block elements. Why are they exhibiting like that? Because more unpaired electrons they have to be created. Next difference between the two is heavier members exhibit higher oxidation state, highest oxidation state, in fact. Like, you have tungsten, the last one, chromium, molybdenum, tungsten, this can exhibit the highest oxidation state. In that particular group, whichever is the highest oxidation state, they will be able to do it. Whereas in the p block element, in non-transition element, the heavier member cannot. Like in every group we have discussed, in 15 group bismuth cannot show 5, right? And in 16th group polonium cannot exhibit the highest oxidation state. In 14th group lead cannot exhibit 4 oxidation state. Why? Because of inert pair effect. Clear? So you will write down two differences between the two. Suppose you are asked which transition element does not exhibit variable oxidation state. You will write down scandium. It shows only one oxidation state, that is 3. It will show only 3 because its configuration is 3D1 and 4S2. So all three will take part in the the bond formation. Next question, a very very important question. It's a very important question. E0 for copper 2+/Cu is always positive. Give reason. Normally any E0 value, if we are deciding, we decide summing up all the energy values. Means if the element is in the solid state, that should be converted to gas, gas to ion, ion to aqueous ion. Right? The energies involved are sublimation, ionization and hydration. Ionization and sublimation are positive, but hydration is negative. Whenever they are saying it is more positive, means the positive components would have been more than the negative component. So that you have to keep in mind, right? So it says that high energy, if you have to write down, you will write down this way: high energy required to transform from this to this, actually mainly from here to here, because this, if you are talking from Cu2+ means one more electron will be lost. So we can say the positive energy values are more. You can say, instead of sublimation, you can use the term atomization. Right? So you will say that the enthalpy of atomization and the ionization energies are too high and the hydration energy liberated is less. So the overall value becomes more positive. And you already have studied in electrochemistry, more positive value means it will act as cathode. Cathode means reduction. Reduction means the lower one is more stable than the Cu2+. That is what they mean to say. Right? Another very, very important question, children. This one, chromium. Yeah, the question is Cr2+ is reducing, whereas Mn3+ is oxidizing, though both have D4 configuration. Now, first you write, this is reducing. Reducing agent means itself is undergoing oxidation. This is oxidizing means itself is undergoing reduction. In this form, both have D4. But in the oxidized form, this will have D3 and this will have D5. Both are stable in their respective thing. But because this is having D3, D3 means T2G3, which is more stable than the half-filled configuration. So you will write, because chromium acquires T2G3 configuration, which is more stable than D5, this is reducing and this one is oxidizing. So you will write like that, Okay, if they are asking one is oxidizing and reducing, in this case you will not compare anything like this. You will just say it is reducing because in the oxidized state it is stable because of T2G3. This is stable because of D5. Right? Next question is this. Suppose you're asked questions like this. E naught value for Mn, this is more negative, zinc is more negative, Ni is more negative, then what? Now, negative means they will act as anode. Anode means they will be undergoing oxidation. Oxidation means the higher positive one is more stable than the lower one. Right? Now, this is more stable. Obviously, we know the configuration of Mn2 plus 3d5, Zn2 plus 3d10. That means they are more stable because of d5 and d10 configuration. Their ionization energies will be low. If you start from Mn and you try to form Mn2 plus, it will try to lose electrons readily and acquire d5 configuration. So it's ionized. The negative component is more, means either the hydration is too high or ionization is too low. So in Mn and Zn, they can lose electrons readily, so their ionization energies are less, whereas in nickel it is more negative because hydration enthalpy is more negative. Clear? You might be asked some questions like this also, that why the E naught value for this is more negative, this is more positive. You just see, if it is more negative means higher oxidation state 1 is more stable. More positive means this is more stable. More positive means this is more stable. More negative means this. Always you try writing their configurations. Right? Scandium 3 plus configuration is 3D0. If it is D0, D5, D10, very stable. What about this one? Iska right side is more stable. Why? Because this is having D10 configuration. Iska bhi right is more stable. That is 3D5 configuration. Its left is more stable for this because in this state it is D5. So you will write their configurations and then see. Right? So this is how you will answer the questions. Why it is more negative, positive, you can answer on the basis of the configurations. Another very important, these 3-4 questions are very important in D block. This is very important. Another important question. Cu plus compounds are unstable in the aqueous solution. Sometimes they give a equation or you write down the equation on your own. They are unstable. That means Cu plus state is not stable. Cu2 plus is more stable than plus. They mean to say this. Now, obviously, if you start from Cu, you know first Cu2 plus will 1 will be formed. Then Cu2 plus will be formed. That means if we start from here, first ionization energy will be less, second will be more. So that means this formation in terms of ionization energy, this is not favorable. Then what is more favorable for this one? If I compare hydration of the two, this will have more hydration enthalpy. So its more negative component exceeds than the positive component. So you will write like that, the stability of this Cu2 plus aqueous is more because its hydration energy of Cu2 plus is more than Cu plus. It compensates even for the second ionization energy of Cu. Right? So if you are comparing Cu plus, say why it is going and forming Cu2 plus, in terms of ionization, this fails. But still it is being formed. That means its hydration energy is very high. And that too in aqueous solution they are saying. So you will write higher ionization energy of Cu2 plus over Cu plus compensates for the higher second ionization energy of copper. Next question. Ability of oxygen to stabilize the highest oxidation state exceeds halogen. Or you can be also asked like that, Mn with oxygen can exhibit +7 oxidation state, but with fluorine it is exhibiting only this. Why? Because oxygen has the ability to form multiple bonds. It can form multiple bonds with the metal. So that is the reason why it can exhibit the higher oxidation states with the oxygen. Next question. Oxidizing power of the species is increasing in this order. There are 2 points you can write. One in terms of the oxidation states. Vanadium oxidation state is 5, here 6 and here 7. Second point means you can say ki higher the oxidation state, more is oxidizing power. Or you may write because they're acting as oxidizing agent means themselves are undergoing reduction. When they are undergoing reduction, they must be getting reduced in some species. So that is what they want to say. Increasing stability of the species in which they are getting reduced. That means when they are getting reduced, they might be forming the species which are more stable. So this is getting reduced into Mn2 plus, which is very stable. D5 configuration. So you'll write down 2 points. One, more the oxidation state, more the stability, more the oxidation state, more the oxidizing behavior. Second, increasing stability of the lower species in which they are getting reduced. Next, out of Cr2 plus and Cr3 plus, which is a stronger reducing agent? You will write the configuration of them. Both are undergoing, acting as reducing agent means that themselves are undergoing oxidation. This will get oxidized to 3 plus, this into 3 plus. In this state it is D4, in this state it is D6. So in the other state it is D5 and chromium becomes D3. If you are asked to compare which is more stable, D5 or D3, then you will write down D3. Why? Because in D3 it is T2G3. T2G3 is, say it is D5 here, T2G3 is having still lower energy. Lower the energy, more the stability. Sometimes you're asked questions like this. Any species can be given and you're asked to calculate the magnetic moment. Now, magnetic moment, the formula is this. Mu is equal to root under root n into n plus 2 Bohr magneton. Any species, I've written only 4 examples, but you can be asked any species. You will write the configuration of the atom first, remove the electrons from the valence shell first, and then write down their configurations in the ionic state. Then you see how many unpaired electrons they have. Just put the unpaired electron here and then find out whether they are para or diamagnetic. Right? So, if you compare here, Mn is having 5 unpaired. So, you'll put the value for 5, N value 5, and then you'll get the magnetic moment as this. Scandium and zinc, in their ionic state, they have 0. That means these two species are diamagnetic. They do not have any unpaired electron. Right? So, its magnetic moment would be 0. Chromium, if you write the configuration, D4 you are writing. Right? It is not D4. I suppose if you write, it is D4 because it was 3D5, 4S1. Correct, it is D4. 4 means 4 unpaired. So you can just put the N value as 4 and calculate. So any magnetic property you can find out whether they are magnetic, para or dia. Right? Now, another variety of the questions which can be asked is this. Any species can be given and you are asked to find out whether they are colored or not colored. Nothing to worry. You will just write their configurations and see. You'll write down their configurations and see that they are having any unpaired electron or not. If they have D0 or D10 configuration, then they will be colorless. If they have even one unpaired electron, they will be colored. Got it? So these are their configurations in the ionic state and you can check all of them are having unpaired electron. So they are all colored. Suppose you are asked like that, scandium 3 plus, zinc 2 plus, they do not have any unpaired electron. This is D0, this is D10. So both are colorless. Zinc salts are all colorless. They are white colored salts. Right? Okay, another question is why transition elements are mainly used as alloys, used for making the alloys. The answer for that, just now we have studied the radii part. Their size, atomic radii is almost same. They are all similar in size. Because they are similar in size, they can replace each other, very easily. Right? So like copper is mixed with gold or silver can be mixed with gold to make the ornaments. Why? Because they have all nearly the similar size. So if this is the crystal lattice, one atom can go away and the other one can take the place very easily. So because of the similar size, they are used for making alloys. Okay, so children, today in this video we have discussed all about D block elements.